A single user request hits Google's servers. A user is looking for search results. Maybe they're looking for cat pictures. In order to deliver those search results, that request will have to hit several different internal services on the way to delivering a user response. These different services work together to satisfy that user request. And all of those services need to communicate efficiently, they need to scale, and they need to be secure. Services need to have a consistent way of being observable, allowing for logging and monitoring among those different services. And services need to have a proper management system for security. Since every service wants these different features, like communication and load balancing and security, it makes sense to build these features into a common system that can be deployed to every server. Louis Ryan has spent his years at Google working on service infrastructure. During that time, he's seen massive changes in the way that traffic flows through Google. First, there was the rise of Android and all of the user traffic from mobile phones. And second, there was the rise of Google Cloud Platform, which meant that Google was now responsible for nodes deployed by users outside of Google. These two major changes, mobile and cloud, led to an increase in the amount of traffic and the type of traffic. All of this traffic leads to more internal services communicating with each other. How does service networking change in such an environment? That's one thing we're going to discuss today. Google's adaptation to these new networking conditions was to introduce a service mesh. A service mesh is a network for services. It provides observability, resiliency, traffic control, and other features to every service that plugs into it. Each service needs to plug into the service mesh. In Kubernetes, services connect to the mesh through a sidecar. And let me explain the term sidecar, because this is pretty important for people who are learning about Kubernetes. Kubernetes manages its resources in pods, and each pod contains a set of containers. You might have a pod that's dedicated to responding to any user that is requesting a picture of a cat. The pod abstraction is dedicated to this. But within that pod, you not only have the container that is going to help you serve that cat picture, you not only have this application container, you also have other sidecar containers that help out that application container. You could have a sidecar that gets deployed next to your application container that handles logging, or a sidecar that helps out with monitoring or network communications. And if you're using the Istio service mesh, which is what Louis works on at Google, then that means you're using a sidecar called Envoy. Envoy is a sidecar that's called a service proxy, and it provides configuration updates, load balancing, proxying, and lots of other benefits. We've done some shows about Envoy if you want to check those out. But if we get all of those features out of Envoy, like if we get a load balancer, proxying, we get all these benefits out of the sidecar proxy container, why do we need this other abstraction, this service mesh? Well, that's because it's helpful to have a tool that aggregates and centralizes all of the different communications among these different proxies that are deployed as sidecar containers. So every service gets a sidecar for a service proxy, and every service proxy communicates with the centralized service mesh. Louis Ryan joins this episode to explain the motivations for building the Istio service mesh and the problems it solves for Kubernetes developers. The next 2 weeks are devoted exclusively to the world of Kubernetes and the surrounding projects. And if you are looking to learn more about these projects and you want to get some exposure to our past episodes, you can check out our apps for iOS or Android, where we have all of our episodes, all 650 episodes. The podcast players that you'll find in the App Store are only going to give you the most recent 100 episodes, but these apps have all of our episodes, including our old episodes about Kubernetes, if you're looking to get an introduction to it. And with that, let's get on with this episode of Software Engineering Daily. Azure Container Service simplifies the deployment, management, and operations of Kubernetes. Eliminate the complicated planning and deployment of fully orchestrated, containerized applications with Kubernetes. You can quickly provision clusters to be up and running in no time, while simplifying your monitoring and cluster management through auto upgrades and a built-in operations console. Avoid being locked into any one vendor or resource. You can continue to work with the tools that you already know, such as Helm, and move applications to any Kubernetes deployment. Integrate with your choice of container registry, including Azure Container Registry. Also, quickly and efficiently scale to maximize your resource utilization without having to take your applications offline. Isolate your application from infrastructure failures and transparently scale the underlying infrastructure to meet growing demands, all while increasing the security, reliability, and availability of critical business workloads with Azure. Check out the Azure Container Service at aka.ms/ACS. That's aka.ms/ACS, and the link is in the show notes. Thank you to Azure Container Service for being a sponsor of Software Engineering Daily. Lewis Ryan is one of the lead developers on Istio. Lewis, welcome back to Software Engineering Daily.
Hey, thanks for having me.
You are a principal engineer at Google, and I saw you give a talk at QCon about some of your historical experiences at Google and how those experiences impacted and led to you starting the Istio project. And so for many years, you've been working on API infrastructure at Google. And what this means is HTTP traffic comes in, and this is the layer at which traffic is routed and distributed to different services. It's load balanced. Give a description for the architecture at Google that you have spent your years on. What goes on at the API infrastructure layer?
Right. So, like most API infrastructure products, there's some proxy in the path between the client and ultimately the service that implements the features. If you're going to read a file out of Google Cloud Storage, or you're going to, try and read your schedule out of Google Calendar, there's a variety of things that have to happen when, somebody outside of Google calls a service that runs inside of Google. Right? You have to authenticate who they are, and there's a lot of different ways things can be authenticated based on the context from which they call. You have to enforce policy on that traffic. Make sure that a particular consumer isn't exceeding their quota or exceeding the amount of money they're able to pay for a service. You have to ensure that they're conforming with the terms of service. There can be some variety there. They have to have signed the terms of service in many cases. So there's a lot of these kind of cross-cutting concerns that need to be implemented in this proxy layer before the traffic actually makes its way all the way to the service backend. And you want this to live in the proxy because you don't want all of that code living down in each individual service, right? It's a lot of behavior, and it can change quite rapidly. And the service behavior should be decoupled from that lifecycle. So it's very common in API management to use proxies to do these types of things. Not just inside of Google, but I'm willing to bet hard dollars that every other big company that has an API product is doing something like this. The majority of the time. Certainly, all the commercial enterprise API management products sell proxies.
That term proxy, could you explain what that means, and also explain what the term reverse proxy means? Because I think there are some people who are listening who are a little less familiar with these terms.
Okay. So proxy is essentially a process that receives traffic from the network and forwards that traffic to somewhere else after having done some work on the traffic. Right? So it's basically just an intermediary in the network. And there could be a variety of different types of proxies. And mostly the types of proxies are named after the network topologies in which they work, and also to some degree how they work. A reverse proxy is generally a proxy that receives requests for lots and lots of different services, and then forwards that traffic to lots of individual services internally. So all the clients talk to one proxy instance, or basically replicas of that proxy instance. And then those proxy instances talk to lots of distinct things internally. So from the outside perspective, the proxy looks like, it's n different things, when in fact it's just one actual physical thing. But internally, all the traffic is routed to distinct services. Mm-hmm. And there are other types of proxies, forwarding proxies, gateways, etc., that have slightly different topologies.
So in your talk, you were talking about this API layer, and you gave some milestones in how things changed at Google in response to changes in the external world. So, for example, when smartphones came around, it really changed the amount and the type of traffic that you were receiving at that API layer. How did the introduction of the smartphone change the API topology?
So, in the world before smartphones, right, most API traffic was driven by dynamic web pages, right? We all remember Ajax. So, you tended to have, let's say a product like Gmail, it would have its own API that was consumed by the UI. And so they were very closely coupled, and their APIs they were effectively in the same trust domain. So they didn't need an awful lot of functionality in terms of those kind of cross-cutting behaviors I mentioned earlier. And then you had APIs that were designed for public consumption, but there weren't that many of them, right? They were based on, the products that were, the web available products. So there was an API for, importing contacts into Gmail or reading information out of Calendar. When mobile came around, right, you had basically a vast explosion in client experiences, all packaged up in these things called mobile applications. So now you had a mobile application which is a crossword puzzle, or a mobile application which is, there's so many examples, it's almost kind of hard to keep track. Your banking application. The way those mobile applications would work, right, they would store some state on the device, but they also needed to access services on the back end. And this kind of precipitated a massive explosion in the need to create APIs that were effectively externally facing, right? Because they now had a slightly different security model than traditional web-based APIs. They looked much more like, customer-facing APIs, and in many cases they were, because sometimes, an application would use APIs from multiple different vendors. So these APIs needed all these facilities around quotas and rate limiting and security. But what really happened was just the vast number of them, and some of them were incredibly popular, right? They drove huge amounts of traffic. So it was kind of this hockey stick moment, not just in how many APIs were being launched at Google, because there was just a huge increase in the rate, but also how much API traffic was being received in total. Right? It used to be that all the API traffic we received was because of small enterprise integrations for, email, calendar, kind of back office apps or productivity apps. And now you have, people playing games, and these games need APIs, and there's, 100 million people doing it.
So the increase in the volume of basically the number of different APIs you were serving, that sounds like a problem of API management. It doesn't necessarily sound like the traffic volume is necessarily any different than the type of traffic volume that you might be handling from just the search API. I mean, the volume going to the search API was significant. It's just that now you had this explosion in the cardinality of APIs. Am I understanding things correctly?
So I think we had a bit of both. So we absolutely had an explosion in the cardinality. There was also something of an explosion in the amount of traffic, though not. What really happened is that traffic shifted from rendering web pages to serving APIs. Right. So any infrastructural investments that had occurred in, massive scale web serving shifted over into massive scale API serving. There wasn't, orders of magnitude increase in the net amount of traffic for any particular kind of functional area, but it shifted in its dynamic.
In this new world with the increase in cardinality and perhaps increase in volume, you did build some supporting technologies inside of Google. And so, by the way, if this was like what, 2006 or 2007, sometime around then?
So I joined in 2007, and I worked on social networking for about 18 months, and then I started to work on API infrastructure. Mm-hmm. This was, between 2007 and 2010.
Okay, got it. And so what were the types of supporting technologies you built for this change in environment?
So it used to be that, people, when they built APIs at Google, they were just embedding libraries in their services. So the first transition was getting people over to the kind of proxy model I just discussed, where there was a team that built an API management proxy and then gave all these APIs, these cross-cutting behaviors, and that allowed more APIs to launch faster. Right. So that was really just facilitating the acceleration of the API launch process.
So I believe you eventually built a control plane. Can you explain what a control plane is?
So in API management, there's really two things going on when you receive an API call. Right. One is, any transformations or things you need to do with the data that's in transit. Right. So you may need to receive an API call, it's in one form, the internal service expects it in a different form, you have to do the conversion, and then you send the data along. And then there's a separate kind of parallel set of concerns, which is, what are all the policies that I want to enforce in this traffic? How do I extract telemetry from it? How do I report that telemetry? And you can actually decouple those two things. And that's what we did. So we created a proxy, which is the data plane, and then we have a control plane, which implements all the policies. And the proxy would just simply ask the control plane, what should I do when I receive this API call? Should I let it go through? Should I reject it? Should I do some subtle combination of those two things? And there's a fair amount of complexity in those things. But essentially, we were separating those two concerns out. The primary reason why we separated those concerns was for stability and performance reasons. Proxies work better if they're really dumb. The less work they have to do, the faster they can go. And so the more you can take out of the proxy, the more traffic you can shove through the proxy. And so being able to separate those two things and scale them differently, allowed us to have a better resource profile, to serve traffic faster, and also to reason about the behavior of the system a little better. It also allowed us to accommodate some additional use cases. In particular, when you have API calls that lead to long-running operations, you may still want to enforce policy as those operations continue.
Just as like we've explored in other areas like big data, for example, Google was tackling the same problems that the rest of the industry is tackling, I guess, 10 years, or in this case, something like 7 years, 8 years before they became open sourced and proliferate throughout the rest of the industry. And we're going to eventually get into discussing Istio, which the model of which looks very similar to this control plane and data plane dichotomy that you're describing. But there's a few more historical moments that informed how your own view of API management shaped the development of Istio that we should explore a little bit. So, the first shift was the mobile change. And then, as you said in this talk at QCon, quote, the cloud happened. What does that mean?
So, while mobile traffic, or the mobile revolution, I guess, dramatically increased the number of APIs and did shift some traffic away from the web, cloud really represents a massive shift in the amount of traffic. Right? So now you have clients running on VMs that are on the same physical network effectively as the services they're calling, when they're calling a different vendor like Google. And they're not just, like, let me get my contacts out of calendar now. It's your Memcache, it's your, big table, right? It's these low-level infrastructure APIs that have to run at massive scale with very low latencies, and applications are extremely chatty when they call them, right? So you're talking about APIs that are consumed, 2, 3, 4, 5 orders of magnitude more than a kind of typical web or integration API might be. And so that scale, right, was radically different than what we were, had been serving with the prior stack. And while the prior stack worked reasonably well at the scale that it was targeted at, now you end up in a situation where you have, some class of APIs that are maybe serving hundreds of requests a second. And then you have other classes of APIs that are serving millions of requests a second. And it does not make any sense whatsoever to have those two things impact each other, right? You want to separate them because they have extremely different scaling requirements. And you also don't want a failure mode in one API to impact all the other APIs. And so going through a centralized proxy, you start to get those types of effects, right? You have the proxy becomes a single point of failure and that single point of failure affects APIs regardless of what their traffic patterns are. And that's not what you want. So we wanted the ability to be able to say, look, on a service-by-service basis, we want to be able to decouple them from all the other APIs. And so we moved into a sidecar model where basically each service gets its own proxy. And those proxies are actually co-located with the service itself. So they scale horizontally with the service. They're not impacted by a proxy failing on some other service. So there's a much stronger layer of separation. And also by adopting the sidecar model, we get a better kind of network path topology into the service itself.
This episode of Software Engineering Daily is sponsored by Datadog. Datadog integrates seamlessly with container technologies like Docker and Kubernetes, so you can monitor your entire container cluster in real time. See across all of your servers, containers, apps, and services in one place with powerful visualizations, sophisticated alerting, distributed tracing, and APM. Start monitoring your microservices today with a free trial. And as a bonus, Datadog will send you a free t-shirt. You can get both of those things by going to softwareengineeringdaily.com/Datadog. That's softwareengineeringdaily.com/Datadog. Thank you, Datadog. So the V1 model, before you moved to this sidecar model, was traffic comes in, it gets load balanced across different instances of a service, and the proxying happens where exactly? Where did the proxying happen in the V1 model?
So in the V1 model, which was the thing before I started working on it, all this was done in library code running inside the service itself.
Oh.
So in some ways, the V1 model and the V3 model are much more similar than the middle one. Right? They're both, right? There's no centralized proxy. Right? All the traffic goes from the client effectively direct to the actual service itself. Or there may be other proxies sitting above in the stack, but they're kind of more generic infrastructure than API-specific proxies.
So in the V2, where does the proxy sit exactly?
So in V2, the proxy is a middle proxy, right? A client calls it, so it's one network hop, and then there's another network hop where it goes to the service backend.
I see. So is that basically a load balancer?
Yeah, so proxies are very frequently load balancers.
I see.
They almost always are load balancers.
Okay, I see. So this proxy was a single point of failure. Actually, we had a pretty good show recently about load balancers, and this seems to be what happens is they become single points of failure if you're not careful. So you were able to negate this by moving the proxying layer into the sidecar model, where each, I think you can do this two ways. You can have, well, I guess, do you have a sidecar for each instance of a service, or do you have a single sidecar for? I guess you have to have a sidecar for each instance of the service, right?
Yeah, for each instance.
Right.
So if we have a service and it's running 10,000 jobs, it has 10,000 sidecars.
Mm-hmm. Yes, and then this control plane API. Does that also have redundancy built into it?
So it's a little less redundant because its needs are very well codified behind an API. So what we do have is that the sidecar proxies are able to continue functioning if there are intermittent failures when calling the control plane.
Okay.
And we try to codify those failure modes into the API so that the sidecar proxy can either have degraded but still functional behavior or continuing functioning behavior, even if the control plane is temporarily unavailable.
Mm-hmm. So as you move to this control plane, this post-cloud model with the sidecar, how are the protocols changing around this time? Because I know Google's had protocol buffers. I think gRPC was developed eventually. Mm-hmm. But what were the changes at the protocol layer that were happening around these changes in traffic volume?
So up until cloud, standard, JSON REST or even REST and XML would probably meet most people's performance requirements, at least met the requirements of Google's public-facing APIs. As soon as you're using an API to talk to something like Memcache or Bigtable or really any storage system or systems that have latencies close to memory latencies, then JSON parsing actually becomes a very noticeable component of the observed call latency. Also, wire density starts to matter quite significantly. JSON is not a particularly efficient representation of data on the wire. Even with compression, and compression also contributes to latency. So there's a variety of concerns there. And so, Google at the time had decided to invest in, building out gRPC to facilitate, launching these infrastructural APIs that we were building, and also helping codify some interesting development models and some API use cases that were hard to do with traditional JSON and REST. So aside from the basic efficiencies and latency improvements you get with using gRPC and protobuf, gRPC, for instance, also supports streaming, and not just unidirectional streaming, but bidirectional streaming, right, which can be a big efficiency win for certain classes of workloads. So Google had committed to building out a number of services with gRPC, and so we needed the API infrastructure to be able to handle that. And so, our API proxies fairly quickly added gRPC support because gRPC is effectively just an evolution internally of Stubby. And the API proxy was already converting JSON REST calls into gRPC or Stubby calls, depending on what the internal system was using at its protocol layer. So we built out, for instance, technology that makes it easy to convert gRPC calls into JSON and REST calls, and build that into the proxy, so that we could give people two different flavors of the same API automatically. And that's actually something that we've open sourced.
Now, around this time, this is when Google's cloud business started to develop, I believe, and there was what you call a convergence of the internal systems and the cloud. So security and network and reliability, I guess the concerns that you would need for the cloud business began to overlap with what you would need for the internal business. Describe what was happening.
Right. So, when your clients are on the same physical network as the services that you're offering them, obviously they effectively have the same latency and performance requirements as the internal, consumers of those same services, right? So there was this kind of natural effective convergence of, what people's expectations are of the system, and we want to facilitate, external clients, having the same features and benefits that internal clients had. So we want to make sure that it's easy for them to call the services, that they perform as well as internal use cases are able to consume those services, that they have the same security and authentication, authorization, abuse prevention models. So there's this kind of natural convergence because Google had built, solutions internally to help solve those problems for its own use cases, right, where we have internal clients calling internal services. And we just wanted to kind of naturally bring those other features to market, whereas before we had just kind of been, throwing services over the wall. So there was this kind of performance and scale convergence, a convergence in kind of operations management, and also in how people think about securing services, how they think about controlling access to data, all those different types of concerns. And the trends we see in the cloud industry have very much been along the lines of, we're basically, us and all the vendors building services that map features that we had built out for internal infrastructure.
And as these shifts that occurred in mobile and cloud increased the volume and the number of services that you had running, I think you pointed out in your talk that it became a challenge in and of itself to have Google get an understanding of what its own network topology was, to be able to observe and visualize what's going on in the network. How does that discussion relate to the discussion of proxying and API management?
Yeah, so Google has a lot of infrastructure that we're pretty disciplined internally in telling teams using this infrastructure to build our services. So we have a lot of uniformity, right? We all use the same libraries to build servers, to build clients, to describe how servers and clients are supposed to talk to each other, to do load balancing, all those types of things. And it was still kind of a challenge within Google to kind of, understand the topology of systems, to be able to trace calls. But we had built out tools that had done a lot of those things for us. And you've seen a lot of those kind of tools come to market. I mean, Google published, I guess, the Dapper white paper many years ago, and now there's Zipkin and Open Tracing and Lightstep and all those types of companies. So, we had done a reasonable job with those tools, enough to make ourselves fairly happy internally. But what was more of a challenge when we had cloud customers now basically consuming our infrastructure, they need the same types of insights. And they need insights that span not only their services, the ones that they built and consume for themselves, but also mixtures of, consuming their own services and consuming our services. And so, being able to provide people a holistic view over their service dependency topology, when that topology spans things running on premise, things running on cloud, services provided by a cloud provider, right? The things get a little bit more complicated.
Mm-hmm. I think we've given people an understanding of the historical context in which Istio was developed. You had all this experience with the API management of Google in those days of burgeoning traffic and increases in traffic, I should say. And now people that are developing their own companies on infrastructure that looks like that of Google's, stuff like Kubernetes, they have similar needs. They're getting an expanse of lots of different services that they're working with, and there are things that they want out of every service. And as you point out in this talk, if you're not careful, you can end up just bundling all of this application logic into your actual app, and that's a lot more cumbersome than standardizing on what you want out of every service and putting it in a sidecar. The sidecar pattern is often implemented with a container, so you have a container that sits alongside your services container, and it does these things that every service wants. So what do we want out of every single service? What are the standards that we want to have?
Right. So, if you think, microservices aside, in any endeavor where people are building services that are talking to each other, right, there's a few kind of standard things that you probably want the network to take care of for you. So let's take HTTP as an example here, because a lot of people write service-to-service communication using things built on top of HTTP. You probably want something that's going to handle retries for you. If a service returns temporarily unavailable or service unavailable, you probably want that traffic, the HTTP request, to be tried somewhere else or tried again. And so retry logic is a very common behavior that people end up writing in code. And it's something that the network could quite easily do for them. Then also you might want to write a piece of code that says, well, if this HTTP call is taking too long, I want it to stop because I need to go do other things, or I need to kind of serve some information back to the user. And so I can't make them wait forever. So I need to have some limit. So you want a timeout. Again, a very common behavior that's written in libraries. And there's a kind of a longer list of these things as topology gets more complex, or you want more load balancing features, right? Or you become higher traffic, you'll want load balancing features. You might want circuit breaking. You might, if you're running a big system, you might want to do kind of chaos testing, right? Where I'm going to deliberately inject faults into my network and see if my application continues to function. And again, these are things that people would have built into libraries. And that really starts to pile up. And it really, really piles up, when you have lots of application development teams all writing in different languages, all implementing those same essential features in a different way. Mm-hmm. Because there are plenty of examples in kind of SRE lore of poorly implemented retry logic or timeout logic causing thundering herd problems.
Oh. One thing you didn't mention there, but you had spent a lot of time on this in your QCon talk, was security. What do we want out of every service in terms of security?
So I think when services or workloads talk to each other, they want a couple of different things. So one, the server wants to know who's talking to it. Right? At least some idea of who's talking to it, because it probably wants to enforce policies. Conversely, the client wants to know that the server it's talking to is actually the server it thinks it's talking to. And so you need this kind of mutual trust model to fulfill these requirements. At least, speaking specifically about workloads within the data center. Because if you don't have some form of mutual trust, right? I mean, if a client is talking to a server, it's possible that somebody may have, brought up a rogue server, registered it in the service registry, and now the client's talking to what it thinks is the real server and sending it, privileged user information, when in fact it's scraping all that information and sending it to some nefarious entity. Conversely, the server wants to know, this is a client, it's a client whose identity I can validate. That identity is allowed to perform certain tasks and not allowed to perform certain other ones. And it would be very nice for application developers if they didn't have to build all of that themselves over and over and over again. Because it can actually be quite complicated. And if you get it wrong, then you have gaping security holes. And there have been many notable examples of that over the years. So you'd like the network and the kind of workload orchestration system like Kubernetes to help you with these problems. Right? You'd like the workload orchestrator to basically, when it runs workloads, be able to give them identities that they can use when they communicate with other services. And so these are the properties that I think you want. You want the network to basically enforce that those identities are properly propagated and validated. And you want the orchestrator to make sure that workloads have identities and that those identities can be used with the network.
If you are building a product for software engineers or you are hiring software engineers, Software Engineering Daily is accepting sponsorships for 2018. Send me an email, jeff@softwareengineeringdaily.com if you're interested. With 23,000 people listening Monday through Friday and the content being fairly selective for a technical listener, Software Engineering Daily is a great way to reach top engineers. And I know that the listeners of Software Engineering Daily are great engineers because I talk to them all the time. I hear from CTOs, CEOs, directors of engineering who listen to the show regularly. I also hear about many newer, hungry software engineers who are looking to level up quickly and prove themselves. And to find out more about sponsoring the show, you can send me an email or tell your marketing director to send me an email, jeff@softwareengineeringdaily.com. And if you're a listener to the show, thank you so much for supporting it through your audienceship. That is quite enough, but if you're interested in taking your support of the show to the next level, then look at sponsoring the show through your company. So send me an email, jeff@softwareengineeringdaily.com. Thank you. So I think people who want to know more about implementing Istio in Kubernetes deployment can obviously listen to the last episode that we did. But just to put some of that into this episode, can you describe the relationship between... So we've got a control plane. We've got this control plane API that has certain functions that it provides, and then we have a sidecar proxy that sits alongside each instance of our service, and it does certain things. Can you just give an overview of the relationship between the sidecars and the control plane API?
Right, so the control plane API is really the thing that, tells Istio what you want the behavior of your network to be. Right, so how you want to route traffic, what policies you want to enforce on that traffic. Right, and the control plane API is designed to be a place for both, service developers and operators to be able to get their job done. In particular, operators, because it gives them a lot of tools that they didn't really have before, right, where they can influence the behavior of traffic in a much more fine-grained way, or they can impose policies that don't require the application code to change. Mm-hmm. Envoy is the sidecar which really is designed to implement those policies. So let's say the control plane API says, well, I want Envoy to round-robin load balance across, all the backends for a particular service. Then the control plane API, an operator will write a rule that specifies that. That rule will basically be synthesized by a component in the system called Pilot, which will then deliver that configuration down to Envoy, which will then basically make that rule effective. So Envoy as a sidecar, is really a logical extension of the application that just happens to sit out of process that implements the networking behavior that you want. And it does that in a few different ways. So one, it obviously affects the routing of traffic, so what we call the data plane, how traffic gets from service A to service B. But it also integrates with the policy layer at runtime, or so that as traffic goes from A to B, that we can check policies on requests, on connections, and things like that. And so that's really the relationship. The control plane API really is an API that's just focused on enabling operators and developers to control the behavior of the network. If you look at, classical SDN systems, right, they have an API that allows you to control the physical topology of the IP network. Well, the control plane API in Istio allows you to control the topology of both the layer 4 network and also the layer 7 network.
One of the aspects of Istio is that it's built in the context of Kubernetes, but it is platform agnostic. Can you explain what that means?
Right. Whenever you run services, you're probably using something to orchestrate how you run them. Kubernetes obviously has done very well in that space, particularly in scheduling and orchestrating services run as containers. But workloads run in lots of places. They run on my laptop. They run on VMs that are brought up manually. They run on Mesos. They run on Docker Swarm. Right? There are lots and lots of ways of running workloads. What we roughly term orchestration systems. And most companies of reasonable scale tend to be using multiple of these things. In fact, it's very hard to think of an example customer where they aren't using more than one of these things. And so Istio needs to be able to work in a world where the workloads are orchestrated by lots of different systems. And those systems also often control how services are registered for things like DNS or console or other kind of endpoint discovery systems. And also where their services span distinct physical networks or different IP namespaces. And so Istio has to be able to kind of stitch all of those things together. So while we did ship Istio, a kind of fully functional version of Istio working with Kubernetes first, because it had such great traction in the market and was a fairly easy platform to integrate with, we don't require it. So it's totally fine to use Istio where all your workloads are running on VMs, or where all your workloads are running scheduled by Nomad, or where all your workloads are running on hardware sitting on premises. Istio actually doesn't really care how the workload is run, as long as you can meet certain integration requirements.
So that agnosticism extends to the things that people can integrate with Istio. So if I want to have a monitoring system, I can use Prometheus. I can plug in Prometheus. I think Prometheus actually comes with it by default, but it's easy to swap out Prometheus with other stuff. I think the same goes for Zipkin as my distributed tracing tool of choice. I can swap it out with other distributed tracing tools of choice. Can you describe the APIs that you want to expose within Istio and where you want to expose those so that people can mix and match the different plugins for their operations?
Right. So if we have this kind of baseline of, sidecar proxies are able to run everywhere associated with their workloads, what those proxies do is they extract information from the traffic as it flows through the network. And they call a component called Mixer, which enforces both policy checking, right, to gate whether that traffic is allowed to proceed or not, and also to receive telemetry, right, which it can then forward to telemetry collection systems like Prometheus. So Mixer is kind of the standardized integration point in Istio for integrations. It's if you want to write a plugin that integrates with Active Directory to do ACL checking, then you can do that, and you should do that in Mixer. If you want to send your telemetry to Datadog instead of Prometheus, you can do it there. So it's this kind of nice, neat integration point that we kind of codify for people and make it easy for them to integrate into, while still allowing them to see an awful lot of information about the totality of the behavior in the network. And so what we're doing with that particular project, Mixer, is working with different vendors to have them write plugins so that at some point, right, you as an operator of your company's services can just take a bunch of this stuff off the shelf and integrate it and configure it to meet what your particular deployment production requirements are.
So the mixer is this point of integration, and the control plane is gathering this data from the different sidecar instances. How aggressively does the mixer pull that data from the sidecars, or does the sidecar push the data to the mixers?
So generally it pushes. So in the case of pure telemetry, the sidecars will tend to, batch data for a period of time and then report it, right? Just for efficiency reasons. In policy checks, right? If you don't want an API call to go through or a service,
you want to know now.
You want to know now. So, you can obviously call mixer one-to-one. That's not particularly efficient. So we provide ways to help Envoy cache the results of those policy decisions. Because the one thing you can say about policy decisions is very often they repeat. One of the things, in our production experience is that services tend to make the same call over and over again very quickly. And so policy checks actually cache very well. And so we put a lot of effort into making sure that policy checks are cacheable by Envoy. And so that, reduces the load on Mixer. It allows us, in some cases for Mixer to do more complicated policy checks. And it also makes the system more generally stable. Mm-hmm. Right? The Mixer is not a single point of failure in the kind of traditional sense. If Mixer goes down, the system will actually keep running for some period of time.
What is the architecture of the control plane API?
So it's in some ways very similar to Kubernetes API architecture. We have a standard set of API resources that configure the different components in the system. They get written into storage by the control plane API. And then the different components, the runtime components, pilot, mixer, and the auth kind of control plane piece, are effectively watching the storage system, bringing those pieces of configuration into memory and making them live. So it's fairly simplistic.
I see. And were there any particular resiliency tools that you had to build from scratch, or were you able to just take stuff off the shelf or recycle things from Kubernetes to maintain the reliability of that control plane?
So it's the control plane API itself actually doesn't need to be very reliable. What really matters is the APIs between the sidecars, the control plane runtime components. Right, that's the thing that actually affects availability. There's two types of problems or availability problems. One is you don't need to change the behavior of the system, and can you maintain the system at its current behavior without having failures? And then another class of problem, which is can I change the behavior of the existing system? And that's the kind of divide between the control plane API and the runtime. You're usually much more invested in the runtime environment being stable, because that's the thing that's affecting the actual services.
So if the control plane is down, the things that maybe won't work so well for me are if one of my sidecars does a check for authentication. Okay, the request to the control plane fails, but I can use one of my cached authentications, hopefully, and then if I can't send my telemetry data to the control plane API, but that's not the end of the world. I can still run, and the control plane is down, so I can't send new config out to my proxies, my sidecar proxies, but it's not the end of the world because my current configuration is probably just fine. So the control plane doesn't necessarily need to be insanely reliable.
Right. So maybe, if you kind of look at the standard Istio diagram, we have what we call the control plane API. That's really just the configuration API, and that doesn't need to be reliable, right? Because that only affects your ability to change the configuration of the system, right? It's totally fine for that to be 2 nines, right? It's the control plane runtime API that, when Envoy talks to Mixer or when Envoy needs to talk to Pilot, that should be much higher availability. And there are things that we do within that, like caching within Envoy, to allow it to go from 3 nines to 4 nines to 5 nines.
Mm-hmm. I guess I have a little bit of trouble understanding why wouldn't you make the control plane API more reliable?
Well, we do. I mean, we work very hard on making it as extremely reliable.
Okay.
But As you go from systems that are trying to achieve 3 nines of reliability to 5 or 6 nines of reliability,
Okay.
a lot of things start to come into play. It's all about refinement of that.
What does change? Tell me about the architectural differences between a 3-9 system and a 5-9 system.
So a 3-9 system, you might, classically, I want one of my components to be horizontally scalable, right? So instead of running one instance of Mixer, you might run 3 or 5 or 50 or 100, right? And that's pretty easy to do. And that, it might get me up to 3 nines. It might even get me up to 4 nines. But it probably won't get me to 5, 6, or 7 because there are other things that can happen, right? So the network connectivity between the sidecar and Mixer might have a problem. Right? It might just be a very niche little corner of the network, that's having packet loss, right? And so calls are timing out. That's the level of refinement where, having a cache inside Envoy, so, that even if that policy check call is only actually physically getting through to Mixer like 1 in 30 times, for that one proxy on that one instance of that service, you're still able to rely on the cache to deliver the policy result. Right? Because, when you're up into, people often measure, system reliability in terms of units of time. If you're up into 4 nines, right, you're talking about, minutes and seconds out of a year, right, of available downtime. And, if you had, let's say, 10, jobs running a particular service, and one of them loses network connectivity for 10 minutes, right, you could start to violate your SLA. It's availability in depth, right? You have to do all the things.
Okay. So I know we're up against time, but, in this talk, you gave these 2 milestones, the mobile traffic and then the change in cloud traffic. And then, since that time, Google has really been a little more open with at least some of their technologies in terms of how aggressively they've gone into open source. And then obviously there's lots of managed services. But is there anything that you're seeing from the inside where you're like, oh, this is going to be the next big source of crazy traffic that's going to change the API layer? Like maybe one thing that comes to mind is just the stuff that can go on in distributed machine learning systems. Like that almost seems like, whereas with something like mobile, it's like at least you're gated by how aggressive the external users are. With something like distributed machine learning, if Google says, we've got these machine learning jobs, and if we just have extra resources, we can allocate those resources to machine learning jobs. That means that like the demands on your system are just going to scale, infinitely. So are there any, upcoming challenges to the API infrastructure that you're seeing on the horizon?
So, I mean, there certainly are. Machine learning is its own special world, right? Almost where you have lots and lots of these. Forget about microservices or nano services. You have these TPUs, which are computational units, which make calls between each other on physical hardware that's dedicated towards that. Running a sidecar proxy between those two things would make absolutely no sense. Okay. So, at a certain scale and a certain latency requirement, proxies don't make any sense. And now you really have to push functionality all the way down as far as you humanly can into the application layer. And things start to get pretty crazy. At a certain scale, you're probably going to want to use very, very dedicated, even hardware dedicated libraries to do certain classes of things. I think the sidecar model is going to actually scale very well for the overwhelming majority of typical enterprise and average storage use cases. So that's a pretty long runway, frankly. And so I think what you'll see is just a segregation in between this kind of 90th, the 90% of workloads which, don't need dedicated hardware, and, the 10% of workloads that do, but the 10% of workloads might represent 90% of the traffic.
Okay.
If you look at what's going on in machine learning and people building dedicated hardware for that, it's pretty clear, right? There's just no way without building for the hardware that you're going to be able to compete.
By the way, does that stuff start to get difficult for you? Because I did one show about distributed deep learning, and it was probably the hardest show that I've done. And I just got so confused so fast. You're a principal staff engineer, I think, but so I don't know. Do your skills start to be tested in that domain?
Oh yeah, no, I won't say my eyes glaze over, but I can go read a white paper, that's published internally that describes how some of this stuff might work, and I get it at the high level, but it's a bit like reading, a brief history of time.
Right.
Yeah, it's a great read. Yeah, this all totally makes sense to me, and then you give me the postgraduate master's thesis textbooks on quantum mechanics, and I'm lost.
Right.
There's just a cliff of specialization that occurs, and it definitely occurs internally too. So, yeah, there are limitations to where I think Clint Eastwood put it best. A man's got to recognize his limitations. That definitely applies to software development too. And, while I think Istio will be very useful for a lot of people, there are definitely some people who I am not pitching Istio to for good reason.
Got it. All right, Louis. Well, it's been a pleasure talking to you. Thanks for making time at the end of a Friday. I really enjoyed your talk at QCon. I recommend people check it out. I'll put it in the show notes. And I'm really excited about Istio, and I plan to continue reporting on it astutely.
All right. Well, thanks for having me on. It's always been fun. And hopefully people find the QCon material interesting and, engage with the community, try it out, and hopefully it does them some good.
Simplify continuous delivery with GoCD, the on-premise, open-source, continuous delivery tool by ThoughtWorks. With GoCD, you can easily model complex deployment workflows using pipelines and visualize them end-to-end with the value stream map. You get complete visibility into and control over your company's deployments. At gocd.org/sedaily, find out how to bring continuous delivery to your teams. Say goodbye to deployment panic and hello to consistent, predictable deliveries. Visit gocd.org/sedaily to learn more about GoCD. Commercial support and enterprise add-ons, including disaster recovery, are available. Thanks to GoCD for being a continued sponsor of Software Engineering Daily.
Wow!